Okay, gentlemen, getting towards the end of chemistry. So this is pretty much the second last section. You're going to do thermochemical equations and calorimetry, which is what I'm going to cover today. And next week, we're going to do uh, heat and changes of state, and that'll be it. So this section, one more section next week, and we will be done. There will not be a quiz, just so you know. We're just going to kind of run out the year and try to teach you a couple things. I may do a bit of acids and bases that last day, just to kind of give you definitions. So this is the PowerPoint you're going to go through today, or at least you should. I just wanted to point out that there is a section on, let's see here, heats of formation, which is a little further down. So if you see the section on heats of formation, I'm not going over that this year. So don't worry about the heats of formation part. If you want to learn about it, please read about it. It's something that will come up later in chemistry if you continue on, but it is not something that you need to know for this year, because it's kind of one of those things that we usually would have learned, but due to circumstances is not there anymore. So you have to worry about heats of formation. We're going to learn about how we measure energy in chemistry today. So first I'm going to talk about calorimetry, which is actually how we measure energy, or more accurately, how we measure the flow of energy, because we can really only measure where energy is moving. We can't measure it unless it moves. You can't take something, even if it has energy, and just look at it and tell how much energy it has. You have to see that energy go from one place to another. It's one of those things where we can measure the effects of energy, but we can't measure energy directly. And when we measure the effects of energy in chemistry, we're talking about things getting hotter or colder. We're talking about temperature change. Energy in chemistry is measured as heat primarily. So again, we're going to be measuring it in joules or kilojoules. We will not be using calories for this. For calorimetry, we'll just be using joules or kilojoules. The tool we use is a calorimeter. Calor means heat in Latin. Meter means measure, so heat measurer. And it's a pretty simple device. There are more complex ones, but basically, a calorimeter is an insulated container in which you put water and a thermometer, and then whatever sample you want, whatever reaction you want to measure or sample you want to measure for energy transfer. If it's something that can't happen in water, like chemical reaction that can't happen in water, there's a special type of calorimeter that has a little chamber in here where the reaction can take place. So say you wanted to find out how many calories were in a piece of potato chip, you could burn that potato chip in a calorimeter. You need a little combustion chamber. And then by measuring how much the water increased in temperature, you can actually work back and figure out how many calories are in that. So how does it work? Well, it's pretty simple. The basic idea is heat can go into or out of a system and into the surroundings. What we're trying to do is capture that heat in the surroundings, which is going to be the water, and hold it there for a while so that we can measure it accurately. That's why it's insulated, and usually there's a lid on it, because we want to keep all the heat in the water, all the heat that's there in there as long as possible so we can measure it. Of course, if you leave it out long enough, it will eventually escape and go to room temperature no matter what, even if it's really well insulated. So it's a pretty simple idea. So this is a very, very simple calorimetry idea. So we start with 100 grams of water, which is 100 milliliters of water at 25 degrees Celsius in, a foam coffee cup would work well for this. That's actually what we would have used in class. And into that, you're going to put a hot sample of metal, for instance, or a cold sample of metal. It really doesn't matter. So we're starting without chemical reactions, but you could run a reaction in here and work the same way. I just want to give you an example with metal. So you got a hot piece of gold, because why not use gold, since this is all online and theoretical. And the gold's 100 degrees Celsius, boiling water. Let's say that gold just came out of a pot of boiling water, because why wouldn't you boil your gold? If you put it in there, what is going to happen, and all of you know this, is the gold is going to cool down, and the water is going to heat up. And what's really going on is the heat from the gold is going into the water. The energy spontaneously flows. Heat spontaneously flows from warmer to cooler objects. So the heat will flow out of the gold into the water until they both reach an equilibrium temperature. At which point the flow of heat stops, or at least it stops in net. There's still heat going into and out of, but at the same rate. So heat goes out. That would be an exothermic process if you're talking about the gold as a system, and that's how I'm defining it. So this would be an exothermic process. We're talking about the water as the surroundings. And it turns out both things would reach a temperature, both the water and the gold, of 25.23 degrees Celsius. And I actually figured that out just using math, and I looked up the specific heat of gold. So just by knowing the specific heat of gold and the specific heat of water, which you should also know, the specific heat of water is 4.18 joules per grams degrees Celsius, and I mentioned that in the last video. That's actually one of those numbers I use so much I have memorized, so that's always going to be burned in my brain. But I looked up the specific heat for gold, and you can actually figure out all of that using the math. And I want to skip to that really quickly. This is the math I did to figure that out, and it looks really complicated. But basically, if you take these two equations at the top, Q equals mc delta T, and the Q of the system is negative Q of the surroundings, so whatever energy enters the system exits the surroundings, or whatever energy exits the system enters the surroundings, which is just a fancy way of saying all the joules that left the gold, all the joules of energy that left the gold had to go into the water. If it left the gold, the water gained the energy. If the gold happened to be really cold, the energy would flow in reverse, but we can't make or destroy energy. So all that energy has to be there. So if it's going out of the gold, it has to be going into the water. And the reason we have, again, it's insulated is because we're trying to trap it in there for as long as possible to get as accurate a measurement as possible. So Q of the system equals negative Q of the surroundings, Q just being heat in joules. Remember, heat is in joules. Temperature is an effect that heat has, but temperature and heat are different. Temperature is in degrees Celsius or kelvins, and Q is heat, which is energy in joules. So if you know these two things, you can actually set up an equation. And I just did the water in blue and the golden color, so you can keep everything straight. But knowing that mc delta T of one is the negative mc delta T of the other one, so the Q, I just set Q equal and opposite there. And the other trick you have to realize is that the final temperature for both of them is going to be equal. And this is true of all calorimetry. The final temperature for both the system and the surroundings is equal. You put something hot or cold into a calorimeter, and the water in the calorimeter changes temperature until they both equal. So since you have that, you only have really one variable there then, which is X, that final temperature. You know everything else. You know the starting temperatures of both things, their specific heats, and their masses. So that's just a matter of rearranging the equation and plugging everything in. And it looks like complicated rearranging, but you could all do that if you just follow through this. And I'm not going to go over it step by step, but it is possible. But let's say I ran this in the lab and I didn't actually know what the final temperature would be. All I do is I just measure this with the thermometer, and when the thermometer peaked at 25.23, that's when I call it. So you'd measure, you put in the hot thing in the water's temperature would rise, and you generally would take pretty much the highest reading you get. Because if you let it go long enough, yes, it will come back down to room temperature, but you take the highest reading you get, which would be 25.23 there. So let's say that happened. If I wanted to know how much energy moved from one thing to the other, well, I can figure that out because I know the water went up 0.23 degrees. So the water went up 0.23 degrees. Q equals mc delta T. I now know my delta T. It's positive 0.23 degrees Celsius. So 100 grams times 4.18 joules per grams degrees Celsius, the specific heat of water, times 0.23 equals 96.14 joules. So if you put 10 grams of 100-degree gold into 100 grams of 25-degree water, 96.14 joules will be transferred out of the gold and into the water. The reason it's positive for the water is because it gained those joules, and the reason it's negative for the gold is because it lost those joules. Notice these numbers are exactly equal and opposite. All the joules, all the energy that left the gold went into the water. And let's say I was doing this experiment to find the specific heat of gold. Well, now that I know gold's energy, gold's heat, Q, I can plug in all the numbers I need to find specific heat. So Q equals mc delta T, C, rearrange for C equals Q over m delta T. And I know all these things. I know my Q, it's 96.14, negative 96.14. I know I start with 10 grams of gold. I know the starting temperature of the gold was 100 degrees Celsius, and the final temperature was 25.23. So I know my delta C is negative 74.77. So doing all that math, I find that the specific heat of gold is 0.129 joules per grams degrees Celsius. And that is correct. And you'll notice that is, 1/40th the specific heat of water. It takes a lot of energy to change the temperature of water, which is one of the reasons we use it in calorimeters, because you can get a broad range of temperature measurement, of energy measurements, without changing the temperature too much, without having wild temperature fluctuations. So it gives us a broad measuring range because it takes so much energy to change water's temperature. So that is calorimetry, very basic kind of overview of calorimetry. And again, it's just using this Q equals MC delta T equation. As long as you remember that the Q of the system, whatever you're focusing on, in this case the gold, is equal and opposite Q of the water, which is your surroundings, you're good to go. You just find the Q of the water, find how much energy went into the water or out of the water, and you flip that, and you have exactly how much energy went into or out of the system. The other thing is, remember, water is 1 gram per milliliter. So we're always going to know how much water we start with, and we're always going to know the starting temperature of the water because we set that as part of the calorimeter setup. So I know I had 100 grams of water starting at 25 degrees Celsius. That's a good thing to know. Okay. And again, you can go through all this math. It looks terrible. It's really not. I did it, and I'm not all that bright. So it's basic, very basic algebra. There's not even any polynomials in here. It's just solve for x, basically. There's a lot of letters in here, but you actually know all those numbers, except for that x number. Solve for x, and you're good to go. But that is how I figured out what the final temperature would be. Okay, the other thing I wanted to talk about really quickly is thermochemical equations, and these are pretty simple to understand. Basically, it's a chemical equation, and they add in the heat component. So all chemical reactions have heat that goes into or comes out of them, and all they're doing in a thermochemical equation is showing that. So here's an example: the combustion of hydrogen to make water. Now, it has to be a balanced equation because it's a chemical equation. We work with balanced equations. But 2 hydrogen gases plus an oxygen gas gives us 2 waters, and then plus 483 kilojoules. So it shows the heat energy. So it's a chemical equation that has the thermo component, the heat component, thermochemical equation. And that's all it is. If you have to put heat into the reaction, the heat would go on the reactant side. If you get heat out of the reaction, it goes on the product side. And so if you have to put heat in, that's endothermic, heat going in. So if it's on the reactant side, that means it's an endothermic reaction if the heat is on the reactant side. If it's exothermic, like this one, this is a very exothermic reaction. This is what I did when I blew up those balloons. So this would be the exothermic reaction. I built some water, and we got a lot of heat. We got fire. So exothermic heat is a product. Heat went out. It became a product. There is another way to write this. Instead of writing the thermochemical equation, you can write the regular chemical equation and then what is called the heat of reaction, which is delta H, sometimes a little RXN at the bottom. Sometimes it's just delta H. RXN just stands for reaction. So another way of writing this would be the same balanced chemical equation, but instead of putting plus 483 kilojoules, we would just write off to the side somewhere, delta H of this reaction is negative 483 kilojoules. The reason it's negative, remember, negative heats mean exothermic. This chemical reaction loses or gives off 483, numbers are hard, 483 kilojoules. So it's actually losing that energy. So that's why it's negative. If this were an endothermic reaction, you'd have a positive delta H reaction. And for our purposes, the heat of reaction, also known as the enthalpy change, and regular heat are the same thing. These are all words that are used interchangeably. So don't worry about anything as far as delta H being different than Q. There are some technical differences when you get more advanced into chemistry and start talking about different pressures and all sorts of things like that. Excuse me. But for our purposes, delta H and Q are the same thing. So you could measure this in a calorimeter. You could do this reaction in a calorimeter, see how much it heats up the water. You need a much tougher calorimeter because, you know, explosion. But you could do it, see how much it heats up the water, and get that sort of number out of it, get the heat of reaction out of it. This is kind of an important thing to know. We need to know how much energy we are going to get out of certain chemical reactions. You know, if you're flying a plane, you might want to know how much energy that fuel is going to give you. That might be a good thing to know. If you're, you know, making cement, when they built the Hoover Dam, because the cement, when cement is drying or curing, that's an exothermic reaction, and it has to give off that heat to cure properly. They actually had to put in cooling pipes when they built the Hoover Dam through the cement, and then they filled them back in later so that it could properly cool. And you have to understand the thermochemistry behind that and behind that reaction in order to know how to do that and make something strong instead of something that would have been made out of weak concrete. So that's balanced equation, or sorry, that's thermochemical equations and calorimetry really quickly. Yes, I know this is a fairly quick overview, and I'm just trying to cover some topics by the end of the year. Try to get the worksheet done. I will go over a few problems on the worksheet tomorrow in the next video. So we should be set with that. Have a good day, gentlemen. See you tomorrow.